Find general solutions of the differential equation dy dx plus 2xy squared is equal to 0. The first thing that we'll do is let's subtract the 2xy squared term from both sides, and that will give us dy dx is equal to negative 2x y squared. Now here we notice that our equation is made up solely of products. And whenever we have an equation, a differential equation where the left and right sides are just products or division, that's a good indication that we can use separation of variables. And we're going to move terms involving y's to one side, terms involving x's to the other. So let's first divide both sides by y squared, and we will get 1 over y squared dy dx equals negative 2x. Now, as we want to solve this differential equation, we do need to integrate, and specifically we're going to integrate both sides with respect to x. And we need to pay attention to this term. The derivative of y with respect to x, and as we integrate that with respect to x, through a change of variables, we can simplify this to just be our dy. And oftentimes we'll just go from this step here, mentally think about this intermediate step, and then just for ease of writing, write it as the integral of 1 over y squared dy. Let's bring out the negative here as well. And we can integrate both of the left and the right side as a known integral. So the integral of the left side is negative y to the negative 1 equals negative, okay, we have x squared plus c. We'll distribute the negative, multiply, actually we'll just divide both sides by negative 1. The negatives will cancel. And we get 1 over y equals x squared plus c. Let's get y by itself since this is relatively easy to solve. And we'll get y is equal to 1 over x squared plus c as a general solution to our differential equation. Now at this example, we see that the left side is just dy dx, the right side is a product, so separation of variables comes to mind. We're going to move terms involving the y to the left, keep the terms that are there on the right, and as we do so, that will involve us dividing by secant. But remember that whenever you divide by secant, 1 over secant is the same as cosine of y. So when we divide both sides by secant, that will actually simplify to give us cosine of y dy dx equals 2x. And at this point, we will integrate both sides with respect to x. Remember, whenever on the left side we get the dy dx with respect to x, we're just, through change of variables, rewriting that as dy. So we're just going to immediately write that for simplification here. Cosine of y dy equals the integral of 2x dx. Both these are really well-known integrals. We know the integral of cosine is sine of y. Integral of 2x is x squared plus our constant of integration. Then we can apply our inverse sine function to both sides, and we'll get the simplified y is equal to inverse sine of x squared plus c. So take a moment to look at this differential equation and see if, as it's currently written, can we use separation of variables immediately. Now we know separation of variables is generally used whenever we've got products or quotients, because at that point we can multiply and divide and isolate variables. The issue that I see at this moment is we have a lot of addition, a lot of subtraction, and those can't be isolated as easily to get all the y's on one side, all the x's on the others, and sometimes not at all. But one thing to notice here that might help illuminate our next step is there's a lot of common terms here. For instance, here, the last two terms both have a y squared. So if we were to factor out a y squared, that would leave us with 1 minus x squared. But of course, that was being added to the first two terms of 1 minus x squared. Here I'm going to group. And then we can see factor by grouping applies. I'm going to rewrite the y prime as dy dx. And since we have the common 1 minus x squared, let's factor that out. And we get 1 minus x squared times, factoring out of itself leaves us 1 plus y squared from the second term. And here we see separation of variables can be used because we have exclusively products and quotients. So we can move everything involving an x to one side, everything involving a y to the other. So manipulating this equation, we would get 1 over 1 plus y squared dy dx equals 1 minus x squared over x squared. But here let's simplify. We know 1, the x squared can distribute to both sides of the subtraction in our numerator. So we'll get 1 over x minus 1. And now we can integrate both sides with respect to x. We know that the left side becomes rewritten as the integral of 1 over 1 plus y squared dy, the integral of x to the negative 2 minus 1 with respect to x. This is a known integral formula. This becomes inverse tangent of y plus c. And then we can solve for y by applying tangent to both sides as a function composition, and we'd be left with y is equal to tangent of negative x to the negative 1 minus x plus c. Now in our next problem, we have an initial condition, and we know that will come into play after we found our general solution. We'll substitute in for the input and the output value and then solve for the correct value of c. Now I'm going to quickly rewrite this x prime as our dx with respect to the independent variable t. And as we're working to simplify this, we notice it's not yet a candidate for separation of variables because we can't isolate the x's and t's in immediately our next step. However, to get us along that path, we see that we've got a 3t squared in both terms, so we could factor that out. And that gives us dx dt equals 3t squared factored times x minus 1. And here, now that we have the product, we can divide both sides by x minus 1, and we will have our separation of variables. So we have 1 over x minus 1 dx dt equals 3t squared. And as before, we are going to integrate both sides with respect to our independent variable. In this case, it is t. So we integrate both sides with respect to t. We know the left side simplifies to the integral of 1 over x minus 1 dx equals to the integral of 3t squared dt. The left side is natural log x minus 1 equals t cubed plus c. Now we do need to solve to get x by itself. And before we do that, we might see if we can plug in our initial condition to find out what c is, and then we can algebraically solve for x. So our input is t, and that's 0. So here we're going to plug in a 0 here. Our output should be 2, which is our x. So that gives us ln of 2 minus 1 equals 0 cubed plus c. Ln of 1 is 0. So we end up with the equation 0 equals 0 plus c. That tells us c is 0 for this case. So we have the simplified expression ln of x minus 1 equals t cubed. If we want to solve to get x by itself, we will have e raised to the left side equal to e raised to the right side. And e and natural log are inverse functions. They do cancel out. So we'll get x minus 1 equals e to the t cubed. Add 1 to both sides, and we get our final expression, x equals e to the t cubed plus 1.